So thank you, everyone, for coming. I research battery materials in my work here, but Kent gave a nice presentation last term on battery materials. So I thought I'd switch it up and I'd talk about something new. So I'm going to talk about the electrification of transportation, which has some there are some application of batteries in this topic. So that's why it's interesting for me. And I've had a lot of fun researching it the last week, so I hope you guys enjoy it. The electrification of transportation refers to using electric engines as opposed to combustion engines to power our transportation. But why is it important? Well, we need to reduce CO2 emissions, and we need to maximize efficiencies of our transportation systems. And finally, we want to reduce the dependence on oil so that we don't have to deal with the fluctuations in market price. So CO2 emissions have been steadily rising, and transportation contributes to this. It's the fourth largest contribution to global CO2 emissions. It takes up 14% of all CO2. And what about the energy that it consumes? It's responsible for 28% of energy consumption in the United States and a significant portion of the global energy consumption. Most of that is petroleum. But why? This is a plot I pulled from BP, so an oil company, but this is their projection for available energy resources in 2050. And even they think that we'll have very limited oil in the future. Here we have nuclear energy and solar energy and geothermal, which far outweigh oil and other energy sources. So we need to harness these energy sources, and moving to electric transportation would enable us to do that. The reason I'm focusing, or today I'll be focusing mostly on the electrification of automotives, or cars, because they take up more than half of all energy consumed by transportation. LDV here stands for light duty vehicle, which is cars or light trucks, and that's 52% of the energy that's consumed by transportation. Down near the more efficient side of transportation modes are locomotives or trains, and I'll begin with a little backstory from the electrification of this mode of transport. So locomotives were initially powered by coal or steam, but they went electric as early as the early 19th century. So it shows that it's possible. Of course, trains travel on train tracks, and so we have a method where we have a route to transport the electricity to, while cars have roads and can go off roads that are a little bit more inconvenient. So that's where batteries come in. But trains are a great example of how electrified transportation is very convenient, and this particularly is a tram from Bordeaux. And you'll notice that there are no overhead lines like there are on most tram systems around the world. So it is really a beautiful piece of engineering, and it's something that we should aspire to recreate with automotives. So what about automobiles? This is the fastest electric car in the world, and it goes just about 315 miles an hour. But this isn't really practical. First of all, it's very expensive. We're not going to be driving these around the road. And secondly, the batteries that go into this aren't going to be reused multiple times. They'll use the full capacity of the battery, and they'll destroy it in the process. So what is available to us today? We have, on the lower end of the market, cars that can drive between 30 to 60 miles on a single charge, and they'll cost you roughly 30 or 70,000 pounds. Okay? Yes, this is a Hummer. After Hummer was discontinued, they made an electric version of the car. It's a little bit smaller and has a very reduced range, but it's kind of fun. In the mid-range market, we have the Renault Zoe and the Volkswagen e-Golf. And these will go between 120 and 130 miles on a single charge. And they cost you between 18 and 26,000 pounds. And then on the high end of the market, leading the industry is Tesla. So these are premium vehicles, but they have really remarkable range and performance. The Model S and the Model X can go 300 to 250 miles on a single charge. And although they're premium, they have released a new car for $35,000 US dollars that will have a range of about 200 miles per charge, which is still higher than all other electric vehicles on the market today. And although this is a premium technology, so is the iPhone at one point. But today, the technology is ubiquitous. We all have smartphones in our pockets. And so they made that possible. And we're hoping that Tesla can do the same. A little bit more on the stats of the Model S, their top performing car. They come in several different configurations with different size batteries and different numbers of motors. The fastest of these can go 0 to 60 in 2.8 seconds, which is remarkable. That's faster than most sports cars that you can buy on the market. And then, as I said before, you can go more than 300 miles on a single charge with this car. But when it comes to electric vehicles, the speed and acceleration of these vehicles is not really the main concern. We're more interested in how long the car is going to last, or the durability of the vehicle. So to compete with gasoline cars, we need it to last a long time. And here, Tesla have been collecting data, and they've plotted the capacity fade of the Model S battery against the mileage in kilometers of the car. So a car, on average, will drive roughly 2,000 kilometers a year. That's a pretty high upper bound on that. So from here to London is about 100 kilometers. So in a year, consider doing 20 of those trips or 200 of those trips in a year. That's a significant range. So over about 5 years, or 100,000 kilometers, the Model S battery only fades in capacity about 95%. So that's really great. That's really great performance. And we need to recognize that these cars have this ability already today. But we need to push this a little bit further. The reason, as I've discussed before, are the huge numbers, or the huge CO2 emissions that gasoline cars contribute. Today, there are about 1.2 billion cars on the road, and this will double by 2030 or 2035. So even though vehicle ownership is kind of leveling off in Japan and Europe and the US, in China and India, these numbers are skyrocketing. And if we have this many vehicles on the road, we want to set a precedent now so that we are not stuck with all of these combustion engines when the time comes. Unfortunately today, there are less than 1% of electric vehicles, or there are roughly less than 1% of all vehicles on the road today are electric. So we need to change this. But what about the electric car is better than a gasoline car? For one, it's more efficient. You can get roughly 3 times the number of miles you can get per unit of energy with an electric car than a combustion engine. This is due to limits on combustion. There's a theoretical limit, the Carnot efficiency of combustion engines, that relies on the temperature difference between the hot and cold reservoirs in an engine. And even though you can kind of push that with better combustion engines, there's still a limitation on the temperatures that you can get to in combustion engines. People are working on new ceramic engines, but this work has been going on for a really long time. And there is question about the efficiency of using electricity, even though the prices are much lower than oil, there are still many places today where electricity is generated by dirty sources, burning coal, etc. But they do it on a much larger scale in power plants. And so by the time it reaches your car, your electric vehicle, to charge your battery, you still get a better efficiency for the same energy. So I've focused on electric cars today, but I did promise this would be a talk about electric transportation. But already there are electric buses on the road, and there are electric boats on the oceans, and there are electric trucks that will help you move your house. And just the other day, there was a solar-powered plane that flew across the Pacific from Hawaii to California on a single charge using nothing but sunshine and batteries. So looking into the future, what will electrification of transportation require? We need to consider the cost of this transition and the scale at which we can make these vehicles, and finally, the technologies that we'll need to develop them. And as you all know, I'm obsessed with batteries, so I'll start there. But batteries are a really important part of the electric vehicle. They're one of the more important or most expensive components of the car. And to make them competitive with combustion engines, we need the batteries to last longer. So this is an 18650 cell that you can buy off of Amazon, and it's the same battery that you'll find in the Model S, the Tesla Model S. They have roughly 7,000 of these cells, but we can buy a pack of 2 of them for 13 pounds. So we could make the same energy density that's available in the Model S with these cells for roughly 500 or 600 pounds, just buying cells off of Amazon. But these cells need to be arranged into battery packs. This is one that I've been working on, but the ones in vehicles are much more advanced. They need added coolant and some circuitry to keep them safe. And the manufacturing of the battery pack is actually the most expensive part of it, or it's equal to the price of the individual cells. Cell costs have been going down for a decade, or for years, and energy densities of the individual cells have been increasing. But the cost for battery packs is very uncertain. So even back in 2010, there was a discrepancy between the dollar per kilowatt hour that you expect for a battery pack, and it was between $600 and $1,100 US dollars. So that's quite a broad range, but it's because the manufacturing methods and the scale at which these packs are produced contribute to the cost. So going forward, we need to think about better manufacturing methods and scaling up the production of these cells. I've also been asked about the abundance of lithium on this Earth. Obviously, today we rely on lithium-ion batteries to power electric vehicles. And although there is research into new battery technology, lithium will be the battery of choice for the moment. And it is true that there are 3 producers of lithium today that will sell about 90 to 95% of all lithium on the market. And I looked into this a little bit. Batteries consume almost 40% of all lithium. And this has doubled in the last 10 years. But this is more of an economic concern. So the producers are able to outsell all other new business competitors in the market. So to start up a mine is quite expensive, and then the production of the raw lithium is also quite expensive. So established producers have the advantage for now, but as demand increases, so will supply. We're not going to be short of lithium. It comes from salt flats. You can take brine and evaporate it, and you'll get some lithium out of it. So we don't have a shortage of lithium on the Earth. If we're talking economics, you should really think more about the cobalt that's in the electrode of the battery. Cobalt is the most expensive material that goes into lithium-ion cells. But here on a chart of the abundance of elements on the Earth, we find that it's relatively high up compared to some of the more unabundant elements. And again, this is an economic concern. So as demand increases, so will the supply. We don't have a shortage of these materials. There may be more of a concern for some magnetic materials used in permanent magnets, but we can get around this by using AC induction motors that don't need permanent magnets for the cars. And this is the motor that's used in the Tesla today. So The Guardian says that electric cars will be cheaper than conventional vehicles by 2020. And this will be possible because we're not paying the same price that we do for gasoline. Electricity is a lot cheaper, even with today's oil prices as they plummet. Electricity is cheaper. And over a 5-year or 10-year period, this will add up. And it will make the whole transportation by vehicle a lot cheaper. There will also be new technologies that we can't really conceive the effect of right now, like self-driving vehicles and ride-sharing programs that will really take the responsibility of fueling the vehicles away from the customers. So this will make it easier for the transition to happen. And going forward, what will it really take to make this transition more immediate? Well, it's already happening, but there needs to be improvement in infrastructure. And this will come with increased demand, but the charging points are a real concern. So if you don't have a garage to put your car in, then you have to rely on charging points outside of your home, so maybe at your place of work or on the road, and they need to be in more convenient locations. And finally, we need policies that will favor electric vehicles and make it possible for the infrastructure to develop. Now, I'd like to play you a little video before I end here. It's quite cringy, but it's kind of fun.
Of course, you want speed. Who needs a bike? Try 72 Buick Skylark, 350 small block, and get some serious internal combustion muscle. For all its failings, gasoline power is a cheap, efficient means of transportation. What is that, a matchbox car? Yeah, it'll match your ass. That's what it'll do. I don't think you know what you're picking on here. But as I was about to find out, you challenging me? I sure am. If you want to get more speed and power out of a car, to the track, see you there. You have to unplug your old ideas about what makes cars fast.
David Coe faces off against John Whalen in a 1972 Datsun.
Whoa! What's going on here? 11.8 seconds? It blew my doors off. What?
So this is the fastest accelerating electric vehicle ever made, called the White Zombie. And it'll do 0 to 60 in less than 2.2 seconds. So that's a ridiculous speed. Where acceleration? Ridiculous acceleration. Thank you. That's faster than the quickest road legal car on the market today, the Porsche 918 Spyder, which, by the way, is a hybrid car. Now, I'd like to thank you for listening, and I'm happy to take some questions.